Hi friends, today we will discuss with complex conjugate. Complex conjugate or simply conjugate of a complex number z is equal to x plus iy is defined as the complex number x minus iy and is denoted by z bar. That is, z bar is equal to x minus iy. With xy as a representation of z is equal to x plus iy, the number z bar is also represented by x minus y. That is, z bar is equal to x minus y. Z bar is a reflection in the real axis of the point xy representing z. That is, here we have z, that is xy. Here we have the reflection x minus y, that is z bar. Now, some properties of conjugate of complex numbers. Properties. First one, let z is equal to x plus iy. Then z plus z bar is equal to z is equal to x plus iy. Then z plus z bar is equal to x plus iy plus x minus iy. That is, which is equal to 2x. And z minus z bar, that is x plus iy minus x minus iy, which is equal to I2y. Hence, real part of z, that is x is equal to, we can write z plus z bar by 2, and the imaginary part of z, which is equal to y, is equal to z minus z bar by 2y. Next one, let z is equal to x plus iy. Then z bar is equal to z bar is equal to x plus iy into x minus iy, which is of the form a plus b into a minus b, which we can write as x square minus iy whole square. That is x square minus iy whole square. This is equal to x square plus y square. That is, z bar is equal to x square plus y square. Next we have z1 plus or minus z2 whole conjugate. That is, z1 plus or minus z2 whole conjugate. Z1 conjugate plus or minus z2 conjugate. That is, z1 conjugate plus or minus z2 conjugate. Next we have z1 z2 whole conjugate. Z1 z2 whole conjugate, we can write as z1 conjugate into z2 conjugate. Next one is z1 by z2 whole conjugate. This we can write as z1 conjugate by z2 conjugate, provided here z2 not is equal to 0. Next we go through examples. We are going to express the product 1 by 2 minus 3i into 1 by 1 plus I in the form x plus iy. That is 1 plus 2 minus 3i into 1 by, it is 1 plus I. So, this I can write as 1 by 2 minus 3i into 1 plus I. Usual multiplication in the denominator, we have 1 by 2 into 1 2 minus 3i into I, we have minus 3 plus I into 2 into 1 2 plus minus 3 into 1, which is minus 3. So, this is equal to 1 by 5 minus I, which is equal to 1 by 5 minus I. This 1 by 5 minus I we can write as 1 by 5 minus I into 5 plus I by 5 plus I, where multiplying the numerator and denominator by the complex conjugate of 5 minus I, that is 5 plus I. That is 5 plus I by 5 minus I into 5 plus I, which is equal to 5 plus I by, substituting we get, multiplying we get, it is 5 plus I by 26. This we can write as 5 by 26 plus I into 1 by 26. This is of the form x plus iy. Next we have modulus of a complex number and its properties. Modulus. The modulus of a complex number z is equal to x plus iy is denoted by mod z and is mod z is equal to square root of x square plus y square, which is equal to square root of x square plus y square. Modulus of z conjugate or z bar is equal to modulus of x minus iy, which is equal to again root of x square plus y square, which is equal to mod z. Next we have z into z conjugate. Z into z conjugate is equal to x square plus y square, which is equal to mod z square, which is mod z square. If z1 and z2 are two complex number, then the following hold. That is, mod z1 into z2 whole square is equal to mod z1 into z2 square is equal to z1 into z2 into z1 into z2 conjugate. That we can write as z1 z2 into z1 z2 whole conjugate. Using the result, we have mod z square equal to z bar, which is equal to z1 z2 into, we can write it as z1 bar into z2 bar. Using the property z1 z2 whole bar is equal to z1 bar into z2 bar, which we can write as, which is equal to z1 into, we can write this as z1 into z1 bar into z2 into z2 bar. That is, we have using associativity and commutativity of multiplication of complex numbers, we can write this as, which is equal to mod z1 square into mod z2 square. Hence, we have mod z1 z2 is equal to mod z1 z2 is equal to mod z1 into mod z2. Next, we have mod z1 by z2 is equal to mod z1 by mod z2 provided z2 not equal to 0. Next one we have mod z1 plus z2 is always less than or equal to mod z1 plus mod z2. That is, the absolute value of the sum of two complex numbers is at most as large as the sum of the absolute values of the two numbers. This inequality is called triangle inequality. That is, mod z1 plus z2, mod z1 plus z2 is always less than or equal to mod z1 plus mod z2. Recall that in geometry, triangle inequality states that length of one side of triangle is always less than the sum of the length of other two sides. To prove triangle inequality in the case of complex numbers, we first observe that for any complex number z is equal to x plus iy, we have minus root of x square plus y square that is minus square root of x square plus y square is all than or equal to our x which is always less than or equal to square root of x square plus y square. And we have minus square root of x square plus y square is again less than or equal to y, which is less than or equal to x square plus y square. So that we have minus mode set less than or equal to part of set. Here x is our real part of set, which is less than or equal to mod set. And again minus mod set less than or equal to imaginary part of set, which is less than or equal to mod set. Then we have mod Z1 plus Z2 whole square is equal to Z1 plus Z2 into Z1 plus Z2 conjugate. That is mod Z1 plus Z2. We can write Z1 plus Z2 whole square is equal to Z1 plus Z2 into Z1 plus whole conjugate. We have using the same property, mod Z square equal to Z into Z bar, which is equal to Z1 plus Z2 into Z1 bar plus Z2 bar, or we can write it as Z1 bar plus, which we can write as Z1 conjugate plus multiplying Z1 Z2 conjugate plus Z2 Z1 conjugate plus Z2 Z2 conjugate. This we can write as Z1 conjugate is, we can write it as mod Z1 square plus, here we have Z1 plus, here we have Z2 Z1 conjugate. This we can write as Z1 Z2 conjugate whole conjugate. Here we have Z1 Z2 conjugate plus, we can write Z1 Z2 conjugate whole conjugate plus, again we have Z2 Z2 conjugate, we can write it as mod Z2 square, which we can write as, which is equal to mod Z1 square plus this we can write as, it is 2 real part of Z1 Z2 conjugate, 2 times real part of Z1 Z2 conjugate plus, here we have mod Z2 square, since Z plus Z bar is equal to 2 real part of Z. Now this is less than or equal to mod Z1 square plus, we have 2 times, instead of real part we are taking 2 times mod Z1 Z2 bar plus Z2 bar square, plus Z2 whole square, that's all. That is, using real part of Z is always less than or equal to mod Z. Now this we can write is, which is equal to mod Z1 square plus 2 times, here we can split mod Z1 into mod Z2 bar plus mod Z2 square by using mod Z1 Z2 bar is equal to mod Z1 into mod Z2 bar, which is equal to mod Z1 square plus 2 times mod Z1 mod Z2 plus mod Z2 square. This we can write as, which is equal to mod Z1 square plus 2 times mod Z1 mod Z2 plus mod Z2 square. That is, this we can write as, it is a plus b whole square form. This we can write as mod Z1 plus mod Z2 whole square. Okay. Taking square roots on both sides, we get the triangle equality, that is Z1 plus Z2. Mod Z1 plus Z2 is always less than or equal to mod Z1 plus mod Z2. We now prove modulus of mod Z1 minus mod Z2. That is, next one is modulus of mod Z1 minus mod Z2. That is, modulus of mod Z1 minus mod Z2. Modulus of mod Z1 minus mod Z2, which is always less than or equal to modulus of Z1 plus Z2, which is less than or equal to modulus of Z1 plus Z2. Okay. We write mod Z1 as mod Z1 plus Z2 minus Z2. That is, we can write mod Z1 is equal to mod Z1 plus Z2 minus Z2. This is same as mod Z1. That is, which is equal to mod Z1 plus Z2 plus minus Z2. This we can write mod Z1 plus Z2. Instead of minus Z2, we can write it is plus minus Z2. Both are same. Which is always less than or equal to. This I can write using triangle equality. I can write this is less than or equal to mod Z1 plus Z2 plus what? Mod minus Z2 using triangle inequality. This is again equal to what? Mod Z1 plus Z2 plus mod Z2. Hence, we have mod Z1 minus mod Z2 is less than or equal to mod Z1 plus Z2. That is, mod Z1 minus mod Z2 is less than or equal to mod Z1. It is less than or equal to mod Z2 plus Z1, or you can write mod Z1 plus Z2. So, or you can write mod Z2 minus mod Z1 less than or equal to mod Z1 plus Z2, or you can write minus of, or you can write minus of mod Z1 minus of mod Z1 minus mod Z2 less than or equal to modulus of Z1 plus Z2. Modulus of Z1 plus Z2. Recalling the result that if A and B are two real numbers with A less than or equal to B and minus A less than or equal to B, then we have mod A less than or equal to B. With this combining 1 and 2, that is equations these first and second, we can write modulus of mod Z1 minus mod Z2 is always less than or equal to mod Z1 plus Z2. Now, we prove modulus of mod Z1 minus mod Z2 is always less than or equal to mod Z1 minus Z2. That is, modulus of mod Z1 minus mod Z2 is again less than or equal to modulus of Z1 minus Z2. Modulus of Z1 minus Z2. We have seen that modulus of mod Z1 minus mod Z2 is less than or equal to modulus of Z1 plus Z2. In the previous case, we have what? Modulus of mod Z1 minus mod Z2 is less than or equal to mod Z1 plus Z2. That we have already described. It is less than or equal to mod Z1 plus Z2. Now, replacing Z2 by minus Z2, the above yields. We can replace Z2 by minus Z2. We can write this as it is mod Z1 minus mod Z2 is less than or equal to what? Modulus of Z1 plus minus Z2. Modulus of Z1 plus minus Z2, which implies modulus of, here also we have minus Z2. So, this implies what? Modulus of mod Z1 minus mod Z2 is less than or equal to mod minus Z2, which is equal to mod Z1 minus Z2. So, we have the result. Next, we have an example. Example. For two complex numbers, that is Z1 and Z2, we prove the parallelogram law. That is Z1 plus Z2 whole square. Parallelogram law means Z1 plus Z2 whole square plus Z1 minus Z2 whole square. Of course, we have modulus Z1 minus Z2 whole square. It is equal to 2 times mod Z1 square plus mod Z2 square, which is equal to 2 times mod Z1 square plus mod Z2 square. This is our parallelogram law. This states that the sum of the squares of the lengths of the sides of the parallelogram equals the sum of the squares of the lengths of its diagonal. That is, here we want a parallelogram. This is our parallelogram. So, parallelogram law states that mod Z1 plus Z2 whole square plus mod Z1 minus Z2 whole square is equal to 2 times mod Z1 square plus mod Z2 square. This is our mod Z1 plus Z2. This is our Z1, this is our Z2. So, the proof states that first we take the LHS. LHS we have mod Z1 plus Z2 whole square plus mod Z1 minus Z2 whole square. Mod Z1 plus Z2 whole square plus mod Z1 minus whole square. This is our LHS. This mod Z1 plus Z2 whole square plus Z1 minus Z2 whole square, we can write it as, by using our property, this we can write as Z1 plus Z2 into Z1 plus Z2 conjugate. Similarly, this also we can write as plus Z1 minus Z2 into Z1 minus Z2 conjugate using the property. This we can write as Z1 plus Z2 into Z1 conjugate plus Z2 conjugate plus Z1 minus Z2 into Z1 conjugate minus Z2 conjugate. By multiplying, we can write it as Z1 into Z1 conjugate plus Z1 into Z2 conjugate plus Z2 into Z1 conjugate plus Z2 into Z2 conjugate. This first one, plus here we have Z1 into Z1 conjugate minus Z1 into Z2 conjugate minus Z2 into Z1 conjugate plus Z2 into Z2 conjugate by usual multiplication. This Z1 conjugate we can write as mod Z1 square, and Z2 conjugate we can write as mod Z2 square. So, all together we can write this as, this we can write as mod Z1 square plus, this is mod Z1 square plus 2 times, or you can take this as, it is mod Z1 square plus, we have Z1 Z2 conjugate plus Z2 Z1 conjugate plus, here we can write Z1 Z2 conjugate plus Z2 Z1 conjugate plus Z2 Z2 conjugate we can write as mod Z2 square. This we can write as mod Z2 square. Again here we have mod Z1 square plus, sorry, here we have minus this I am going to write here, this is mod Z1 square plus, here we have minus, it is minus Z1 Z2 conjugate minus Z2 Z1 conjugate plus mod Z2 square. This I can write it as, which is equal to 2 times mod Z square plus mod Z2 square. This is equal to 2 times mod Z square plus mod Z2 square. This is our LHS. So, we begin with the LHS, we got the RHS as 2 times mod Z1 square, here we have Z1 square plus mod Z2 square. Next we have to find the locus of points set satisfying the condition, that is mod Z minus 1 by Z plus 1 is equal to, that we will discuss. That is, we have to find the locus of the point set. That set satisfying what? Modulus of Z minus 1 by Z plus 1. It's not I, it's 1. Z minus 1 by Z plus 1 is equal to lambda. So, Z we can write what? It is, we can convert it as x plus iy. So, this I can write it as x plus iy minus 1 by x plus iy plus 1 is equal to, of course, which is equal to lambda. So, now combining real parts, we have this is equal to x minus I plus iy by x plus 1 plus iy. Here we have squares, here we have squares. So, which is equal to modulus of x minus 1, I am taking real terms together, iy by x plus 1 plus iy whole square is equal to lambda. Here we have lambda square, we are squaring both sides. So, we have it is equal to lambda square, this square is equal to lambda square. So, this we can write x minus 1 plus iy whole square by x plus 1 plus iy whole square, which is equal to lambda square. Now, I can write it as, we can take I square is equal to minus 1. So, I can write this as what? This which is equal to x minus 1 whole square, x minus 1 whole square plus y square, which is equal to x plus 1 whole square plus y square. Here we have, in the RHS we have lambda square. This by simplification we get x square minus 2x plus 1 plus y square. Here we have x minus 1 whole square, and here we have x plus 1 whole square. Expanding, we have x square minus 2x plus 1 plus y square, which is equal to x square plus 2x plus 1 plus y square. Here we have lambda square. So, this implies x square plus y square plus 1, which is equal to x square plus y square plus 1. On simplification, we get x square plus y square plus 1 into lambda square minus 1, which is equal to, no, here we have plus one term remaining, a y square minus 1 plus 2x into lambda square plus 1. We have, which is equal to 0. That is x square plus y square plus 2 times lambda square plus 1 by lambda square minus 1 into x plus 1 is equal to 0. That is, we get this is equal to x square plus y square. Taking similar terms together, we have x square plus y square plus 2 times, here we have 2 times lambda square plus 1 by lambda square plus 1 by lambda square minus 1. 2 times lambda square plus 1 by lambda square minus 1 into x plus 1 is equal to 0. We know this represents a family of coaxial circles. Now, we can define a circle. Consider this set. Z is equal to mod Z minus Z naught is equal to R. That is a representation of a circle. That is the collection of all sets such that mod Z minus Z naught is equal to R. This represents the set of all complex numbers that are at a distance R from the center Z naught. Hence, the set is a circle of radius R greater than 0 centered at Z naught. This is our center Z naught and this is our radius R. This circle is also denoted simply by mod Z minus Z naught is equal to R. This we can write simply as mod Z minus Z naught is equal to R. This is also of circle. In particular, mod Z is equal to 1 is the unit circle. Mod Z is equal to 1. This we call as unit circle. Here we have center is equal to 0 and radius r is equal to 1. Next we have power of a complex number. That is, in order to find product of two non-zero complex numbers Z1 and Z2, polar form is more useful. That is, we can write if Z1 is equal to R1 cos theta 1 plus I sin theta 2 and Z2 is equal to R2 cos theta 2 plus I sin cos theta 2 are the polar forms of two complex numbers Z1 and Z2. Then it can be seen that Z1 into Z2, we can write Z1 into Z2 as R1 into R2. We are taking it in the polar form R1 R2 cos theta 1 plus I sin theta 2 into cos theta 2 plus I sin theta 2 which is equal to, using the product here, we can write R1 R2 into cos theta 1 cos theta 2 minus I sin theta 2 theta 1 sin theta 2 plus I into sin theta 2 cos theta 2 plus cos theta 2 sin theta 2, which we can write it as R1 into R2. By using the formula, we can write as R1 into R2 cos theta 1 plus theta 2 cos theta 1 plus theta 2 plus I sin theta 1 plus theta 2 plus I sin theta 1 plus theta 2. Now we verify that if n is a positive integer and zk has modulus rk and argument theta k, where k varies from 1 to n, then we have Z1 etc. up to Zn is equal to R1 etc. up to Rn into cos theta 1 plus etc. plus theta n plus I sin theta 1 plus etc. plus theta n. The result is true for n is equal to 1 and verified for n is equal to 2. Assume as induction argument that the result is valid when n is equal to m minus 1. Then we have Z1 into etc. into Zm minus 1 is equal to R1 etc. into Rm minus 1 into cos theta 1 plus etc. into theta m minus 1 plus I sin theta 1 etc. up to theta m minus 1. Here we can write R1 etc. into Rm minus 1 cos theta 1 etc. up to theta m minus 1, like that. And we have Z1 etc. We have Z1 etc. into Zm minus 1 into Zm m minus 1 into Zm, we can write this is equal to R1 etc. up to Rm minus 1 into cos theta 1 plus etc. up to theta m minus 1 plus I sin theta 1 etc. up to theta m minus 1 into, that is up to Zm minus 1 into, we have here we have Zm. Zm we can write it as Rm cos theta m plus I sin theta m. So this we can write as, which is equal to R1 R2 etc. up to Rm. Here we have cos theta 1 plus theta 2 etc. up to here we have theta m minus 1 etc. up to theta m minus 1 plus theta m plus I sin, plus next term we have plus I sin theta 1 etc. up to theta m minus 1 plus theta m. Using star we can this result. As a result for the case n is equal to 2. Hence the result is true for m also. Hence the result is true for all positive integers. In particular, when all Z1 etc. Zn's are equal to the non-zero number, Z is equal to R cos theta plus I sin theta. Then we have Z raised to n is equal to R raised to n cos n theta plus I sin theta. That is, we can write Z raised to n is equal to R raised to n into cos n theta plus I sin n theta. This we can write as double star, and is the nth power of set for every integer n greater than 0. When n is equal to 0, with the convention that z raised to 0 is equal to 1 for a non-zero complex number set, it follows that z raised to 0 is equal to 1, which we can write as 1 into cos 0 plus I sin 0. Hence, the result is true for n is equal to 0 also. We know that if z2 not equal to 0, the quotient z1 by z2 can be obtained by dividing the modulo and subtracting the arguments. That is, z1 by z2 we can write it as z1 by z2, which we can write as r1 by r2 cis theta 1 plus theta 2. It is not addition, theta 1 minus theta 2, that is r the arguments. Cis means cos theta plus I sin theta. In particular, with z1 is equal to r cos 0 plus I sin 0, and z2 is equal to z, which is equal to r cos theta plus I sin theta, a non-zero complex number. The multiplication of z is given by z inverse is equal to 1 by z, which is equal to 1 by r cis minus theta. That is, z inverse we can write 1 by z, which we can write as, which is equal to 1 by r cis minus theta, which is equal to 1 by r cos minus theta plus I sin minus theta. Using this, we are going to obtain the expression z raised to n is equal to r raised to n cos n theta plus I sin n theta for negative values. That is, if n is equal to minus 1, minus 2, etc., then with m is equal to minus n, we define z raised to minus n in terms of multiplicative inverse of z by writing z raised to n is equal to z raised to minus m, which we can write as, that is, z raised to n is equal to minus m. This we can write as z raised to minus 1 raised to m, that is, z raised to minus 1 whole raised to m. We can write z raised to minus m as z raised to minus 1 raised to m. This I can write, we have z raised to minus 1 is equal to 1 by r cis minus theta, or 1 by r cos minus theta plus I sin minus theta. This we can write as 1 by r cos minus theta plus I sin minus theta raised to, that is, here we are considering z raised to minus 1 whole raised to m. So, here we have 1 by r cos minus theta plus I sin minus theta raised to m, which I can write as, which is equal to what? Which is equal to 1 by r raised to m, 1 by r whole raised to m. I can write it as 1 by r raised to m. Using the property cos theta plus I sin theta whole raised to n is equal to cos n theta plus I sin theta, I can write this as cos minus theta plus I sin minus theta whole raised to m. That is, cos m minus theta plus I sin m minus theta. Since m is a positive integer, and since the result we have discussed that double star is valid for positive integers, we can write this as 1 by r raised to minus m into minus n into cos minus n into minus theta plus I sin minus n into minus theta. That is, we can replace m by what? Minus n. That is, we can write it as 1 by r raised to minus n cos minus n into minus theta plus I sin minus n into minus theta. That is, here we have replaced m as minus n. Thus, we have r, which is equal to r raised to n into cos n theta plus I sin n theta. Hence, z raised to n is equal, z raised to m is equal to r raised to, z raised to n is equal to r raised to n cos n theta plus I sin n theta is true for any n, that is for positive and negative integers. That is z raised to n. We can write z raised to n is equal to r raised to n cos n theta plus I sin n theta. It is true for any integer n. If mod z is equal to 1, then z is a point on the unit circle. Also, r is equal to mod z is equal to 1, and so has polar form z is equal to cos theta plus I sin theta, and thus the above reduces to cos theta plus I sin theta whole raised to n as cos n theta plus I sin n theta. We can cos theta plus I sin theta, this polar form whole raised to n, this reduces to what? Cos n theta plus I sin n theta. A theorem of De Moivre's. This is valid for any integer n. This can also be expressed in the form e raised to I theta whole raised to n. This we can similarly, this we can write as e raised to I theta whole raised to m is equal to, we can write this as e raised to I m theta for any integer m, or you can take instead of m you can take n for any integer n. Next we have nth roots. Next we have nth root. The possibility nth roots of complex numbers when n is equal to 2, 3, etc. is suggested by the identity z raised to n is equal to r raised to n cos n theta plus I sin theta, which is valid for any integer. We already seen that z raised to n is equal to r raised to n into cos n theta plus I sin n theta. Cos theta plus I sin n theta. This is valid for any integer n. A complex number z is equal to r cos theta plus I sin theta is an nth root of a non-zero complex number a if z raised to n is equal to a. That is z raised to n is equal to a. Written z is equal to, we can write z is equal to a raised to 1 by n, or we can, this we can write as nth root of a. To find nth roots, we write the complex number a in the polar form a is equal to r cos phi plus I sin phi. We can write a is equal to r cos phi plus I sin phi. Then r cos theta plus I sin theta whole raised to n is equal to r cos phi plus I sin phi. R cos theta plus I sin theta whole raised to n is equal to r into cos phi plus I sin phi, which gives r raised to n cos n theta. We can use the identity r raised to n cos n theta plus I sin n theta is equal to r cos phi plus I sin phi. That is, we can write this as r raised to n cos n theta plus I sin n theta, which is equal to r cos phi plus I sin phi. Mark it as equation number 1. Since modulus of cos alpha plus I sin alpha is equal to square root of cos square alpha plus sin square alpha, which is equal to 1 for all real alpha. Taking absolute values on both sides on 1 above yields the relation r raised to n is equal to capital R. Hence, we can write small r is equal to what? R raised to 1 by n. Substituting r raised to n is equal to r in 1, cancellation yields cos n theta plus I sin n theta is equal to cos phi plus I sin phi. Using the cancellations, we have cos n theta plus I sin n theta is equal to cos phi plus I sin phi. That is substituting r raised to n is equal to capital R. We get this. This gives important information about the argument of set, namely that n theta differs this n theta differs from the phi by a multiple of 2 pi. That is, we can write n theta is equal to phi plus 2k pi. N theta is equal to phi plus 2k pi. This k varies from, k can take the value 0, plus or minus 1, plus or minus 2, etc. Or we can write theta is equal to what? Phi plus 2k pi by n. Here k varies from 0, plus or minus 1, plus or minus 2, etc. Or we now search how many integers k produce distinct solutions. With r is equal to r raised to 1 by n and theta is equal to phi plus 2k pi by n, where k varies from, of course, 0, plus or minus 1, plus or minus 2, etc. Z is equal to r cos theta plus I sin theta gives Z is equal to a raised to 1 by n, which I can write as r raised to 1 by n cos phi plus 2k pi by n plus I sin phi plus 2k pi by n. That is, I can write Z is equal to now I can write Z is equal to a raised to 1 by n, which I can write as r raised to 1 by n cos, instead of theta I can write it as phi plus 2k pi by n plus I sin phi plus 2k pi by n for each k, where k varies from 0 to n minus 1. There is a different value for set. 2 pi periodicity of cosine and sine functions shows that when k is equal to n, when k becomes n, we have cos phi plus 2k pi by n plus I sin phi plus 2k pi by n. Instead of k, we can write it as n, that is phi plus 2n pi by n plus I sin phi plus 2 pi n by n, which is equal to cos phi by n plus 2 pi, which is plus I sin phi by n plus 2 pi, or which we can write it as which is equal to cos phi by n plus I sin phi by n. Instead of k is equal to, we can take k is equal to n, which is equal to cos phi plus 2k pi by n plus I sin phi plus 2k pi by n. We can write it as which is equal to this, we can write as cos phi by n plus I sin phi by n. The value corresponds to k equal to 0. Similarly, it can be seen that the value corresponds to k is equal to n plus 1 is that 1 corresponds to k equal to 1 and so on. Hence, there are no more new solutions. Thus, for a non-zero A, there are exactly n distinct complex numbers set. That is, Z is equal to r raised to 1 by n cos k pi by n plus I sin phi plus 2k pi by n, where k varies from 0 etc. up to n minus 1, such that Z raised to n is equal to A. These n values on a circle of radius r raised to 1 by n with center at the origin and constitute the vertices of a regular polygon of n sides. This we will illustrate in later examples. The value of nth root of A obtained by taking the principal value argument of A as phi and k is equal to 0 in equation number 2 is called the principal value of set, which that is equal to nth root of A. Principal value of z is equal to nth root of a. Now we have nth roots of unity. We have discussed about nth roots. Now we have nth roots of unity. Nth roots of unity. To find nth roots of unity, we take a is equal to 1 in the above discussion. Then from the polar representation, a is equal to 1, that we can write it as 1 into cos 0 plus I sin 0. We r is equal to modulus of a, which is equal to 1, and phi is equal to argument of which is equal to 0. So we obtained, that is r is equal to, in the above we can take r is equal to mod a, which is equal to 1, and phi is equal to argument of a, which is equal to 0. So we obtain nth root of 1, that is nth root of 1, we can write this like this, nth root of 1 is equal to cos 2k pi by n plus I sin 2k pi by n. Cos 2k pi by n plus I sin 2k pi by n, where this k varies from, of course this k varies from 0 etc. up to n minus 1. These n values are called the nth unity. They lie on the unit circle. When k is equal to 0, we have nth root of 1 is equal to cos 0 plus I sin 0, which we can get as 1 is the principal value of nth root of 1. Nth root of 1, when k is equal to 0, we get this is equal to cos 0 plus I sin 0, which is equal to 1 at k is equal to 0. This is called the principal, this we can say as principal value of nth root of 1. That is at k is equal to 0. When k is equal to 1, what we have? K is equal to 1, we have nth root of 1 is equal to 2 pi by n plus I sin 2 pi by n. The value of nth root of unity that corresponds to k equal to 1 is usually denoted by omega. We represent, when k is equal to 1, we usually represent the nth root of 1 as, when k is equal to 1, we usually represent this as, by the symbol this, we call this symbol as omega. Hence, nth root of 1 cos 2 pi by n plus I sin 2 pi by n, that is when k is equal to 1, this is equal to, this we represent it as omega. When k is equal to 2, we have nth root of 1 is equal to cos 2 into 2 pi by n plus I sin 2 into 2 pi by n, which we can write as cos 2 pi by n plus I sin 2 pi by n whole square, that is equal to omega square by De Moivre's theorem. That is when k is equal to 2, we have cos 2 pi by n plus I sin 2 pi by n whole square. This we write as omega square, etc. When k is equal to n minus 1, we have nth root of 1 is equal to cos 2 into n minus 1 into pi by n plus I sin 2 into n minus 1 into pi by n, which we can write as cos 2 pi by n plus I sin 2 pi by n whole raised to n minus 1. Similarly, we done it for k is equal to 2. Thus, we have which is equal to omega raised to n minus 1. These values are the vertices of a regular polygon of n sides inscribed in the unit circle with one vertex at the point 1. We represent it as d z naught r. This means This has radius r0 and this disk is centered at z0. This we can represent as set of all sets such that mod z minus z0 is less than r. Radius r and center z0. This is called the neighborhood or r neighborhood of z0. D z0 r, which we call as neighborhood, the set of all set. The set we call as the neighborhood of z0. In particular, D01 is equal to set of all sets such that mod z minus z0 less than 1. Here we have z0 is equal to r01 means center at 0 and radius 1 is called the open unit disk. Set of all sets such that z minus 0 less than 1, open unit disk. A R deleted neighborhood of Z0 is the set consisting of all points set in the R neighborhood of Z0 except for the point Z0 itself. That is, here we have the deleted neighborhood Z0. Deleted neighborhood Z0. Here we have the radius r. That is d z0 r, d of z0 r minus r0 is equal to collection of all sets such that mod z minus z0 less than r and also what z not equal to z0, which is equal to collection of all sets where 0 less than mod z minus z0, which is less than r. This is our deleted neighborhood. Next we have circle. C z0 r. We have circle representation C z0 r. C z0 r means it is a collection of all sets such that z minus collection of all such that mod z minus z0 is equal to r. That is, the circle of radius r greater than 0 and centered at similarly we have the center at the z0 and a radius r. Next we have open set. A set S is said to be open if for any set in S there exists some delta greater than 0 such that D set delta contained in S. That is, D set delta contained in S. Next we have complement of a set. For any set S, we have S complement is equal to C minus S, denotes the complements of set, that is S bar to collection of all set in C such that set it is a collection of set in C such that set not belongs to S, that is S closure. Next we have closed set. A set is closed if its complement is open. Next we have boundary of a set, delta S. The boundary of S is defined as a set of all points whose delta neighbors have a non-empty intersection with both S and S bar for every delta greater than 0. Next we can discuss about closure of a set, S closure. Closure of S is given by S closure is equal to, which we can write it as S union delta S. Delta S is the boundary of a set. Next we have bounded set. S is bounded if it is contained in D0M for some m greater than 0. That is, S, we have this S contained in D0M. That is, S is a subset of some open disk of radius m and it is centered at the origin 0. Next we have compact set. A set that is closed and bounded is called compact. Closed plus bounded implies compact. Disconnected and connected sets. S is said to be disconnected if there exist two disjoint open sets A and B whose union contains S, while neither A nor B alone contains S. If S is not disconnected, it is called connected. Here we have discussed about complex conjugate, powers, roots, and some examples, and about some sets, properties of sets, and connected set, open set, compact set, like that. So, hope you enjoy the session. See you next time. Till then, take care.